Hello and welcome to my video, lesson 2.4 on parallel plates. So this is what it looks like to have two parallel plates. So there's a nice diagram here. We have, first of all, two things to notice, that this symbol here, there you go, this symbol here is a battery, okay, when you're drawing a circuit. And the smaller side is the negative side, so you can see that that's what is happening over here. The larger side is the positive side. Okay. Now D, when we talk about our formulas, is going to just be the distance between the two plates. And yeah, that's kind of what we're going to start with. Oftentimes we're going to have, well, so depending on your type of battery, but if you have just a single AA, you're going to have 1.5 volts. So the positive side, when compared to the negative side, is 1.5 volts. So there's a difference here of 1.5 volts. That's what that means. All right, so let's continue on and just start talking about it before we get to some example questions later. If we have two charged plates, we can create uniform electric fields. So here's our two different charged plates. And if you think back to our last video, we always said that if you have a positive charge, then you'll be pushing things away. So it's always envisioning what happens if there's a positive particle in the field, whereas negative charge always pulls towards, right? So that's what we talked about in the last video. Now here, if it's positive plate and negative plate, if we have put a positive particle inside, well, it's going to be pushed from the positive and pulled from the negative. Now, the really cool thing about this is that we're going to have a uniform electric field. This means that it's the same no matter where we are. If we're here, or if we're here in the middle, or if we're close to the negative, it doesn't matter. It's just going to transfer. So if we're closer to the positive side, we're going to have more of the push portion from the positive side and a very tiny pull. But if we're closer to the negative side, we're going to have a big pull and a very, very tiny push. So yeah, big. Here we're going to have a big push, tiny pull. Here we're going to have a tiny pull, push, and a big pull. And it's always going to be balanced. They're just going to kind of transfer off to each other as the particle travels in the region between the parallel plates. So again, the big idea is it's a uniform electric field, which means that we're going to have a uniform force between the electric field, and if excuse me, and if we have a uniform force, that means we have uniformly accelerated motion or uniform acceleration, which is really important and really useful for many reasons. But F net equals ma is going to be the big idea. Okay, so let's continue going. So there's a couple things we can do with these parallel plates. Potential difference is the electrical potential between the two plates, usually in voltage. This is, the wording is kind of weird here. It's per unit distance or something. So yeah, so the per unit charge. Okay, so this is the potential between the two. It's the voltage. Okay, so when we talk about potential difference, we're talking about the voltage between the two plates, and then this here is the energy, potential energy that you can gain or lose. So this is very similar in concept. Potential energy, electric energy works the same as gravitational potential. Basically, as you move in the field, you can gain or lose your potential energy. So let's go back to this diagram and talk about it for a second. So if we have a positive charged particle up here, okay, then it wants to move down, and it has all of this room to move down. So because it wants to move down and it can move down, it's got all of this potential energy. Once it has moved down, now it's down here, now it has lost its potential energy because it no longer can move in the direction that it wants to move. It's attracted to the negatives. It can't move that way anymore. So it's just going to stop right there. So at the end, closest to the side it wants to be is generally speaking going to be, you know, your EK, and then closer to the side where you've got you know, the room to move is going to be your EP. Just like if you're dropping a ball in Physics 20 or even Science 10. So, same sort of idea, conservation of energy to solve for kinetic energy, or oftentimes straight up for velocity. Okay, current is the rate of the flow of electrons, usually in amps. So this is our formula for it. So we've got 3 different formulas here that are useful in different contexts. So yeah, I is the current, which is in amps usually. Q is the coulombs, the charge, and then T is the time in seconds. Conventional current is backwards and incorrect. Current is the flow of electrons. This is very important. If you Google this, you'll often probably find the American version. The American version is conventional current and it's backwards, and it's also wrong. Okay, Americans are wrong about this. So, but the conventional current is the idea that it's the flow of the positive charge. But we know protons can't leave an atom. That would be a nuclear explosion, or any sort of nuclear reaction would be separating protons or neutrons from the atom. So that doesn't work. But electrons can flow back and forth. We know this from basic chemistry, Chem 20, or even Science 10 when we start learning about Lewis dot diagrams, right? So when you bond these, you can see that the electrons are happy to be balanced or to move. And so that's the electrons moving. Same thing here. Electrons move, not protons, not a positive charge. The negative charge moves. That's it. Okay, and with that said, if it's an electron moving, then we can define an electron volt as 1 eV equals 1.6 times 10 to the negative 19 joules. This is useful to know because it's the amount of energy gained by one electron traveling across one voltage. Okay, so if you put in 1 electron, 1 volt, let's just go up here. So that formula was delta V equals delta E over Q. We just rearranged that to solve for our E. So delta E equals delta V over Q. And honestly, normally I'm kind of skipping all the deltas here. So E equals V over Q. Well, by definition, 1 volt over 1 electron gives us 1 eV, electron volt. It's not spelled right, but whatever. Okay, so you see the idea here. So it makes it nice, otherwise we're going to have a lot of, times 10 to the negative 19s, or a lot of other small numbers that we're going to have to deal with. We don't want to do that, so that's why electron volts are useful. Now, this whole idea of electricity here, it's helpful but not perfect to think about a river. If you think about a river, the height of a river is the voltage. So if you have a high enough river and a high enough drop, then it's actually a waterfall, right? And waterfalls, well, that's what we use to make dams, right? We create our own waterfall, but that's really what we're doing, is we dam up a river to create height. And that's really the energy that we're getting. That's the same thing here. The height is going to give us the energy in a dam. The voltage is going to give us the energy in the particle between parallel plates. Or actually, sorry, yeah, that too, but also within the wire itself. And then the rate of flow of water flow in a river is like the amps in electricity. Okay, it's the rate of water flow, rate of electron flow. Okay, so we have a few different questions to try out. They're fairly straightforward. I highly recommend that you you take a look at the formula sheet to just get used to these formulas here, and also get used to every once in a while you're going to have to go up here and get some information from here or from here or from here. So there's all sorts of places. So just keep in mind you're going to have to look at the data booklet. But let's take a look at this question. Determine the electric field strength between two parallel plates with a voltage of that and separated by a distance of that. So we're looking for field strength. So if we go to our formula sheet, which equation shows us field strength? So it's going to be in this section here, but let's look at which one actually shows us field strength. I'm going to just switch colors. So between parallel plates, that's this one here. So this is the one we're going to be looking at. Okay, you're going to notice that these are all field strength ones, but this one only works for particles. So if it's a particle situation, because the charge, this Q part, is the charge that's causing the field to occur. Now, if we have two parallel plates, we don't have a charge to occur. This one is the particle within the field. So it's different as well in the field. Okay, this one's particle causing, this particle in the field, and this is always for parallel plates. And so is this one, but we're going to deal with that in the next one. Okay, the next example. Okay, so anyways, we're looking at this one right now. So E equals V over D. So we're looking for the field strength. It's just going to be 12 over 3. Now this is not going to be 3, this is going to be 0.03 meters. So that's going to be 4 over 0.01. I'm just trying to do this in my head instead of the other way around. So 400, and this is volts per meter. Or if you remember from the last one, it's newtons per coulomb. So either way is fine here, by the way, but that would be your field strength. Okay, let's take a look at the next one. Find the electrical potential change, positive or negative, when the proton moves from position M to N, given that its voltage change was that. So it's a proton, so we do need to look at some values in here. So a proton is a 1 charge, and whoops. There you go. And we know its mass. 1 charge is just one of these here. So oh, yeah, and we need the formula. It's just 1 charge, that's the important part. But it's this guy here, it's this formula right here that we're solving for. Okay, so voltage equals energy over charge. So we're going to solve this for energy. So energy equals Q delta V if we want. So then given this, we know it's 1 charge. It's 1 positive charge. so it's plus 1, and its voltage was 4.5 volts, and so we can actually just say this is going to be 4.5 EV, electron volts. If you wanted to get it in joules, you could also do that, 1.6 times 10 to the negative 19 coulombs, and then 4.5 volts. Okay, but this is the change. Is it positive or negative? Well, it's actually losing this much potential energy. Okay, why? Because it has moved in the natural direction. It's lost that much energy, it's moved in the natural direction. So if it moved this way, it would be gaining potential energy. Okay, if it moved this way, it's losing potential energy. Losing potential energy. Okay, just two more simple examples to try out. Example number 3, a 2.45 Coulomb charge is traveling past a certain measurement point. Given that the amps used is 0.75 amps, what is the time period of the measurement? So again, we should probably check here, but this is the formula we're going to use. So amps equals charge, so I equals charge over time. So what we're going to do is we're going to rearrange this to solve for our t. So it's going to be t equals q over I, which is going to be 2.45 coulombs over 0.75 amps. And so how long was it? All right, so it took 3.26 repeating seconds. So let's just do 3.3 seconds. Okay, I recommend you pause the video here and try out the last question for yourself and see if you can figure it out. Okay, the last one here is kind of interesting. Determine the maximum speed of an alpha particle if it moves through a potential difference of that. Okay, so what we're going to have to do is recognize if we're looking for maximum speed, what's happening is we're doing our potential change and we're making it equal to our kinetic energy. So the potential change is coming from the formula E equals Q delta V, whereas the kinetic energy is coming from the formula half mv squared. Okay, so with all of this said, we're going to plug those into the conservation of energy formula here. So QV equals mv squared over 2. Keep in mind that those two v's are different. The first one is a capital V, it's voltage. The second one is a lowercase v, it's velocity. And that's what we're looking for, the velocity. So we're going to move some things over. So 2qv over m equals v squared. Now we're going to square root it, so it's going to be 2q capital V over m square rooted equals v. And now we can plug it in. So 2 times, and now this is a little confusing because we've done a lot of good work, but we don't have the charge of an alpha particle, or do we? Yes, we do. We have it right over here. The charge of an alpha particle is 2 times the elementary charge, plus we know the mass over here as well. So this is going to be 2 times, because of the 2 in the formula, and then the charge is 2 times 1.6 times 10 to the negative 19, times the voltage, which was 3,540, over the mass, which was 6.65, I think. Let's just double check that. Yes, 6.5, times 10 to the negative 27. I'll just double check. Yes. Okay, so we get a maximum velocity of 5.83688 times 10 to the 5 meters per second. And then let's just think about sig digs. We've got 4 sig digs there, but we only have 3 sig digs here for the alpha particle information. So it's going to be 3 sig digs, 5.84 times 10 to the 5 meters per second is the maximum speed. Alright, I hope this video helped you better understand 2 parallel plates and charges between them. I hope it helped. Good luck!